Bye.
Okay, my pleasure to welcome our next speaker, Professor Don Howard. Professor Howard is the former director and fellow of the University of Notre Dame Rayleigh Center for Science, Technology, and Values, where he now functions as co-director of the Center's Ethics of Emerging Technologies focus area. He holds a permanent appointment as a professor in the Department of Philosophy. Professor Howard is an internationally recognized expert on the history and philosophy of modern physics, especially the work of Einstein and Bohr. His books in physics and philosophy are Scientific Philosophy, Its Origins and Development, and Einstein as a Philosopher of Science. Today, Professor Howard will be talking about complementarity and decoherence. We are looking forward to your talk. You can start your talk, Professor Howard.
Give me a moment, please, to call up my version of the slides here, if I can.
Professor Howard, hello.
Yes.
You can click on the three dots icon on top of the slides to take ownership and control of your slides.
Let me see.
On the upright.
Up left.
Yes, but I'm not seeing. Let's see. There we go. Okay. Can you see that?
Yes, yes.
Okay. Can you close the, there we go. Excellent, excellent. Well, thank you so much for the invitation to speak with you today. It's a great pleasure. Since time is limited, let's get right to the task. I'm going to be talking today about complementarity and decoherence. And I'm going to make an argument to the effect that a proper understanding of contemporary decoherence theory is enhanced by a proper understanding of Niels Bohr's complementarity interpretation of quantum mechanics. Let me begin here by commenting, well, why can't I advance my slides? Hold on a second. Give me a moment. Let me begin by remarking on this, namely that the talk is based on a paper of the same title that was published last year in a memorial volume for Michael Horn, whose name might be not be well known to everyone, but he is the first H in the very famous CH-SH theorem, the Clauser-Horn-Shimony-Holt theorem, that made possible the experimental tests of Bell's theorem, for which the Nobel Prize was awarded last fall. So Michael played an important role historically in our modern understanding of entanglement, among other things. But to the task of the talk itself, I want to start by asking the question, what is decoherence? And the first thing I will say, as I say to my students all the time, that decoherence is whatever Max Schlossauer says it is. This book of his from about 20 years ago remains I think, the best introduction to the whole topic of decoherence that's ever been written. I also recommend just a second. I also recommend the dissertation that was written 12 years ago by my PhD student, Elise Krull, Quantum Decoherence and Interlevel Relations. And in particular, if you're new to the topic of decoherence, Her chapter entitled Decoherence for the Non-Specialist is a wonderful pedagogical introduction to the theme. So, but let's talk about it from a conceptual point of view. For the purpose of my talk today, the central theme of decoherence is this, that when a system or a system-instrument pair is entangled with a large number of environmental degrees of freedom, the purely quantum dynamics of the interaction with the environment, which means ordinary linear quantum mechanical Schrodinger dynamics, drives the system instrument environment complex into a pure state that is, as they say, observationally indistinguishable from a mixture over eigenstates. And in this way, quantum mechanics itself explains the emergence of what I like to call a simulacrum of classicality, even though in principle the world at all scales remains purely quantum. In addition, it's typical of decoherence that the dynamics of the system instrument environment interaction picks out a privileged basis, which is generically termed a pointer basis or an Ein-selected basis. And in many cases, but not always, that basis will be one close enough to a position basis as to be functionally equivalent to it for all practical purposes. Such a basis is privileged in the sense that it is robust with respect to perturbations. But even among physicists, there's a lot of confusion about decoherence, reinforced by the unfortunate choice of the name decoherence for this approach. The name notwithstanding, decoherence does not produce wave packet collapse. It cannot, because the dynamics is simply linear Schrodinger dynamics. On the contrary, it produces only what I like to call, again, a simulacrum of wave packet collapse. In other words, decoherence does not actually produce genuine decoherence. But the main question I want to ask in this talk then is this: in what precise sense is the pure state into which the decoherence dynamics drives the system instrument pair, in what sense is that pure state observationally indistinguishable from a mixture over eigenstates? And answering that question will require our taking a deep dive into Bohr's complementarity interpretation of quantum mechanics. Let's talk a little bit about the history of decoherence. How old is the idea? Many people think it was born in the work of Dieter Zeh in the 1970s. Obviously, we know that Zurek made important contributions to the development of decoherence in the 1980s. But in fact, the idea is a very old idea, and it goes all the way back to Heisenberg's realization around 1927 that the appearance of definite particle trajectories, such as in a cloud chamber, was a result of environmental monitoring by the supersaturated gas or fluid mixture. The pointer basis for the particle being roughly a position basis, and the pointers being the condensed fluid droplets. And then in the 1950s and 60s, Heisenberg and others, Rosenfeld, Peterson, Grunewald, von Weizsäcker, Ludwig, worked explicitly on Bohr's idea that the dynamics of the measurement interaction, that is the coupling of system degrees of freedom to instrument and environmental degrees of freedom, was responsible for the appearance of classicality in such form as the seeming irreversibility of measurement outcomes. So question now, does decoherence corroborate or contradict Bohr's interpretation of quantum mechanics? Well, it depends upon what we take to be Bohr's interpretation of quantum mechanics. And we need to start with this insight, namely, there is no single Copenhagen interpretation, contrary to what has long been assumed. In fact, there were deep differences between the core members or among the core members of the Copenhagen community. Thus, for example, Heisenberg, Jordan, and others did believe in wave packet collapse and a privileged role for the subjective observer, whereas Bohr, Rosenfeld, and a number of others in that community rejected the concept of wave packet collapse and assumed no privileged role for the subjective observer. So I want to focus on Bohr's version of the interpretation of quantum mechanics. And in order to understand that, we are going to have to understand Bohr's own conception of what he himself termed classicality, as in his famous insistence on the central and ineliminable role of classical concepts in physics. Now, what did he mean by that? Did he mean by that the physics of Newton and Maxwell? Was he talking about the definiteness produced by wave packet collapse? Or did he mean the physics that best describes macroscopic measuring instruments? As you will see, I deny all of these common assumptions about Bohr's notion of classicality. There are many early approaches to explicating the concept of a classical limit. The old Bohr correspondence principle, taking the limit of small h, Ehrenfest theorems, large mass, de Broglie wavelength goes to zero, limit of large numbers of degrees of freedom, lots of ideas for how to think about a classical limit. None of those really panned out very well. So what then is Bohr's interpretation of quantum mechanics? It is, at heart, the thesis of complementarity, and it is based on two premises. One, entanglement is the fundamental novelty of the quantum theory's description of nature. And number two, an objective description of nature requires the employment of classical modes of description, whatever that means. I haven't explicated that yet. Let's start with entanglement. Many people think that the concept of entanglement was only introduced into quantum physics in 1935 by Erwin Schrödinger, but that's actually quite false. I'm not going to go through all of these steps in the history, but I want to convince you that by as early as 1927, it was well established in the core community that entanglement was, as I say, the central novelty of the quantum realm. I'm going to skip a couple of slides here and focus especially on this. The very best evidence that entanglement was taken to be an unavoidable implication of orthodox quantum mechanics comes from Einstein himself. In May of 1927, Einstein gave a lecture to the Prussian Academy of Sciences in which he presented his own hidden variables theory. The talk was turned into a paper, and when the paper was in the proof stage, Einstein found out that there was a problem with his hidden variables theory. And I want to read this one part of a note he added to the proofs where he spells out what he discovered was the problem. He writes the following: I have found that the schema, his hidden variables theory, does not satisfy a general requirement that must be imposed on a general law of motion for systems. Consider in particular a system that consists of two energetically independent subsystems. This means that the potential energy as well as the kinetic energy is additively composed of two parts, the first of which contains quantities referring only to system one, the second quantities referring only to system two. And then he writes, it is well known that the state function for the joint system must be a product of the state functions for the component systems. And he goes on to say, where psi 1 depends only on the coordinates of system 1, psi 2 only on the coordinates of system 2. And in this case, we must demand that the motions of the composite system be combinations of possible motions of the subsystem. The indicated scheme, again, his hidden variables theory, does not satisfy this requirement. In particular, well, we'll stop there. The point is that he was assuming that joint state functions must always be factorizable, which is contrary to the notion of entanglement. But what he found was that his own hidden variables theory was just as entangled as orthodox quantum mechanics. just to give you two other examples of how widespread was the understanding of entanglement at that time. I won't read these quotations, but I'll just mention them. Here is Hermann Weyl writing in 1931 in his book, Group Theory and Quantum Mechanics, where he spells out the fundamentality of entanglement in quantum mechanics in crystal clear terms. Or here is Pauli in his 1933 article on the general principles of wave mechanics for the Handbuch der Physik, where he too writes the same thing. Unfortunately, the equation isn't displaying there for reasons I don't understand, but trust me, it's there in that Handbuch article. So when Schrödinger introduces the term entanglement in 1935, all he's doing is restating what was by that time the commonplace wisdom. Now, why is it important that we understand that entanglement goes all the way back to the late 1920s? It's because, as I said a moment ago in sketching the core ideas of Bohr's complementarity interpretation of quantum mechanics, it's because, as I said a few minutes ago, entanglement is absolutely fundamental for Bohr. How do we know this? Well, let's look at famous words from the 1927 Como lecture, which was published in English in 1928 in Nature. This is the paper in which Bohr first introduces the concept of complementarity. And look at how he begins this. He writes, now the quantum postulate implies that any observation of atomic phenomena will involve an interaction with the agency of observation, not to be neglected. My italics now. Accordingly, an independent reality in the ordinary physical sense can neither be ascribed to the phenomena nor to the agencies of observation. This situation has far-reaching consequences. Again, I won't read the whole quotation. Hamid can share the slides with you, and you can ponder this in more detail later on. But he immediately goes on to present the core idea of complementarity. There's been widespread misunderstanding of those first quoted words, where he says, accordingly, an independent reality in the ordinary physical sense can neither be ascribed to the phenomena nor to the agencies of observation. Many scholars have read that as if Bohr was denying the existence of a quantum reality. This quotation has been the basis for many arguments that Bohr was an anti-realist about quantum mechanics. But of course, that's not what he's saying. He's not denying the existence of a reality. What he's saying is that there is no independent reality that can be ascribed to the phenomena nor to the agencies of observation. That's just his verbal way of saying that when a measurement occurs, the measured object and the agencies of observation, the measuring instruments, become entangled with one another. So entanglement was well understood as early as 1927. It is absolutely fundamental to Bohr's interpretation of quantum mechanics. But now let's turn to the other fundamental question that I said we had to address in order to appreciate what's relevant in Bohr's complementarity interpretation of quantum mechanics. Entanglement is fundamental, but equally fundamental is Bohr's consistent emphasis upon the necessary employment of what he called classical concepts in quantum physics. And the question is, what for Bohr makes a classical concept classical? And most importantly, let's start here. Does this mean that the classical quantum distinction coincides with the instrument object distinction? That's a view that's widespread in the secondary literature. But in fact, that was not Bohr's view. How do we know this? But first, let's just recall some of the famous words that he used. when talking about the necessity of the employment of classical concepts. Here, for example, is Bohr writing in his contribution to the volume Albert Einstein, Philosopher, Scientist in 1949. He writes, "It is decisive to recognize that however far the phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms. The argument is simply that by the word experiment, we refer to a situation where we can tell others what we have done and what we have learned, and that therefore the account of the experimental arrangement and of the results of the observation must be expressed in unambiguous language with suitable application of the terminology of classical physics." Here's another quotation, this from a little-known 1938 paper of Bohr. And here again, I want to read this whole passage to you because this is by far the clearest statement of Bohr's own views about what classicality means. So bear with me. "The elucidation of the paradoxes of atomic physics has disclosed the fact that the unavoidable interaction between the objects and the measuring instruments sets an absolute limit to the possibility of speaking of a behavior of atomic objects which is independent of the means of observation." Let me pause and note that that echoes those previously quoted words from the 1927 Como lecture, where he premiered the concept of complementarity. But then he continues, "We are here faced with an epistemological problem quite new in natural philosophy, where all description of experience has so far been based on the assumption, already inherent in ordinary conventions of language, that it is possible to distinguish sharply between the behavior of objects and the means of observation. This assumption is not only fully justified by all everyday experience, but even constitutes the whole basis of classical physics." There he has just said what classicality means for him, namely that it is possible to distinguish sharply between the behavior of objects and the means of observation. In other words, classicality means the denial of entanglement. Continuing, "As soon as we are dealing, however, with phenomena like individual atomic processes, which due to their very nature are essentially determined by the interaction between the objects in question and the measuring instruments necessary for the definition of the experimental arrangement, we are therefore forced to examine more closely the question of what kind of knowledge can be obtained concerning the objects. In this respect, we must, on the one hand, realize that the aim of every physical experiment, namely to gain knowledge under reproducible and communicable conditions, leaves us no choice but to use everyday concepts, perhaps refined by the terminology of classical physics, not only in all accounts of the construction and manipulation of the measuring instruments, but also in the description of the actual experimental results. On the other hand, it's equally important to understand that just this circumstance implies that no result of an experiment concerning a phenomenon, which in principle lies outside the range of classical physics, can be interpreted as giving information about the independent properties of objects." Well, it seems like we've got a tension here. A dialectical tension, if you will, because on the one hand, Bohr is saying that entanglement is a universal fact about interacting systems as described by quantum mechanics, meaning that the instrument and the object form an indissoluble whole. On the other hand, he is saying that objectivity requires the use of classical modes of description in accounting for measurements and their outcomes, and that seems to deny entanglement. How is this tension, possibly even a seeming contradiction, how is it to be resolved? Well, we can get a clue about the resolution by looking at Bohr's famous description of the two-slit experiment. And I'm going to read to you again some of the text, which is very critical. He's very careful in his explaining what's going on. So in the two-slit diffraction experiment. Remember, you've got two diaphragms. The first collimates the beam, and then the second has two slits, and the photons can go through either the upper slit or the bottom slit. But as you all know, he says that if you fix the first diaphragm firmly to the lab bench, then you get the typical diffraction pattern on the screen at the end. Whereas if you unbolt the first diaphragm from the table and allow it to bounce on a spring so as to be able to measure the vertical component of the momentum of the diaphragm, that enables you to infer the vertical momentum of the particle and thus to predict through which slit the particle will go, in which case there is no diffraction pattern. So what does Bohr say about this? He writes, the principal difference between the two experimental arrangements under consideration is, however, that in the arrangement suited for the control of the momentum of the first diaphragm, that is, movable diaphragm A, this body, namely that first diaphragm, can no longer be used as a measuring instrument for the same purposes as in the previous case, fixed diaphragm, but must, as regards its position relative to the rest of the apparatus, be treated like the particle traversing the slit as an object of investigation, in the sense that the quantum mechanical uncertainty relations regarding its position must be taken into account. Now, appreciate what he's saying here. He is saying that the distinction between the measured object and the measuring apparatus doesn't correspond to something like scale. It's not that the big, heavy diaphragm is once and always a measuring instrument, and that the photon is once and always a quantum mechanical, a quantum scale object. No, what he's saying is that the instrument-object distinction cuts through different degrees of freedom of both the instrument and the object. So again, he says in the arrangement suited for the control of the momentum of the first diaphragm, this body can no longer be used as a measuring instrument for the same purpose as in the previous case, but must, as regards its position relative to the rest of the apparatus, be treated like the particle of traversing the slit as an object of investigation, in the sense that the quantum mechanical uncertainty relations regarding its position and momentum must be taken explicitly into account. But what does this mean? What does it mean to treat that first diaphragm, in this case, as an object of investigation, but only with respect to its position, not its momentum? So there is a cut here, but this is not Heisenberg's variably locatable cut, because Bohr's cut between instrument and object divides not a big instrument from a small quantum object. No, it divides the different degrees of freedom of the diaphragm. Some of them, namely those relevant to the momentum measurement, and only those of degrees of freedom of that diaphragm, those degrees of freedom are being treated classically, and others, such as the diaphragm's position, are being treated quantum mechanically. So again, what could this all possibly mean? So let's think a little bit more about what Bohr says regarding the coupling of instrument and object degrees of freedom necessary in a measurement. So here I am reading from yet another paper of Bohr's, also not well enough known, where he writes, we must recognize that a measurement can mean nothing else than the unambiguous comparison of some property of the object under investigation with a corresponding property of another system serving as a measurement instrument, and for which this property is directly determinable according to its definition in everyday language or in the terminology of classical physics. And then he continues, in the system to which the quantum mechanical formalism is applied, it is of course possible to include any intermediate auxiliary agency employed in the measuring process, since, however, all those properties of such agencies, which according to the aim of the measurements have to be compared with the corresponding properties of the object, must be described on classical lines. Since that is true, their quantum mechanical treatment will, for this purpose, be essentially equivalent with a classical description. That's Bohr in 1939. Remember how I characterized the key claim of decoherence theory, that coupling the object, the instrument, with environmental degrees of freedom, turning on the Schrodinger dynamics for that whole complex, then drives that whole complex into a pure state that is observationally indistinguishable from a mixture over eigenstates. Here is Bohr in 1939 saying essentially the same thing. But still, how do we understand what's going on here? What does it mean that the quantum and classical descriptions of the object and instrument degrees of freedom coupled in the measurement, what does it mean that they must be essentially equivalent? Well, let's think once more about what Bohr says about the ineluctable role of the measurement context. Here's a different remark from Bohr. As a more appropriate way of expression, I advocated the application of the word phenomenon exclusively to refer to the observations obtained under specified circumstances, including an account of the whole experimental arrangement. This is a leitmotif that runs through all of Bohr's writings about measurement in quantum mechanics, that you don't even have a well-posed question until you have specified exactly what constitutes the measurement context. That's a very important point. Or he says in another, back in that 1939 paper, the essential lesson of the analysis of measurements in quantum theory is thus the emphasis on the necessity in the account of phenomena of taking the whole experimental arrangement into consideration in complete conformity with the fact that all unambiguous interpretation of the quantum mechanical formalism involves the fixation of the external conditions defining the initial state of the atomic system concerned and the character of the possible predictions as regards subsequent observable properties of that system. Any measurement in quantum theory can in fact only refer either to a fixation of the initial state or to the test of such predictions, and it is first the combination of measurements of both kinds which constitutes a well-defined phenomenon. Concludes, the conditions, which include the account of the properties and manipulation of all measuring instruments essentially concerned, constitute in fact the only basis for the definition of the concepts by which the phenomenon is described. Well, again, can we put all of this together in a coherent account of Bohr's views on classicality? And the answer is yes. And we do it in the following way. We define the concept of what I call context-dependent mixtures. So define a context as any maximal co-measurable set of joint observables or the corresponding set of joint commuting operators. For any such context, there will exist a complete set of joint simultaneous eigenstates of those operators spanning the joint Hilbert space. And now here's the key technical point. Given the density matrix, WQM, representing the joint pure case, and given a specific context K, as just defined, one can always construct a density matrix. I write this as WK classical CL, representing a mixture over the joint simultaneous eigenstates for that context, such that all of the statistical predictions generated from that context-dependent mixture for the joint observables measurable in that context, they agree exactly with the statistical predictions generated from the quantum mechanical pure state representing the joint state of the object instrument environment complex. Now, this is a theorem. In the case of observables with discrete spectra, the proof of the theorem is actually quite trivial. And I first proved this way back in my doctoral dissertation in 1979. For observables with continuous spectra, the theorem is non-trivial, but in this more general form, it was proved in the late 1990s in joint work by Rob Clifton and Hans Halvorsen, as cited here. Well, let's try to understand what this says. So call to mind the typical Bohm-Bell thought experiment, where you've got two particles that were previously interacting. They go in opposite directions. They pass through Stern-Gerlach apparatus in either wing of the experiment. And depending upon the orientation of the Stern-Gerlach apparatus, you can measure the spin along any axis in either wing. I'm not going to read through all of this right now. And again, the slides are available from Hamid if you want to look at this more closely. But in this case, the pure case density matrix would be as written at the top of the page. And then the density matrix, the context-dependent mixtures, the density matrix for the Z spin measurements in L and R would look like what I've written there. And the density matrix for Y spin measurements would look like this. And you can iterate this for all possible combinations of analyzer orientations in the two wings of the experiment. So what does this mean? And we're getting close to wrapping this all up. Representing the joint state by means of a context-dependent mixture means that with respect to the observables measurable in the given context, one is treating the two systems as if they were not entangled and as if all of the statistics were classical ignorance statistics. It also means that treating the degrees of freedom correlated in that context in a classical manner, hence as if the systems were not entangled, both object and measuring instrument degrees of freedom, with all other degrees of freedom not accurately described by the context-dependent mixture, being treated quantum mechanically. The complementarity between two such classical representations emerges as a trivial consequence of the physical incompatibility of the corresponding contexts. So, noteworthy features of this way of understanding Bohr's interpretation of quantum mechanics. On this view, there is no dualism in the ontology based on scale. It's quantum mechanics all the way up and all the way down. It makes perfect sense of Bohr's contextual notion of a quantum phenomenon. It makes perfectly clear the strict equivalence of the quantum and quote-unquote classical descriptions with respect to the degrees of freedom involved in a measurement. It perfectly reconciles the tension between, Bohr himself noted, between the physical fact of entanglement and the requirement that the kind of classical description needed for objectivity, that treat the object and instrument as if not entangled. And one further noteworthy feature, it also makes clear why quantum indeterminacy is a consequence of entanglement and contextualism, because while the mixture preserves strict correlations within a context, hence strict causality, such strict correlations are not preserved between other degrees of freedom, those not defining the context. So back to complementarity and decoherence. What are the points of compatibility here? Well, both decoherence and complementarity involve quantum mechanics all the way up and all the way down. Quantum mechanics is the unitary fundamental description of nature. And from both points of view, complementarity and decoherence, classicality emerges from fundamental quantum behavior. It is not something fundamentally different in kind. And decoherence confirms Bohr's suggestion that classicality, in the guise of seemingly irreversible marks as the outcomes of measurements arises because of the dissipation of information through the interaction with the environment. Now, a question. What about the privileging of a position basis in decoherence theory? In what sense, if any, is there something inherently or essentially classical in the privileging of a position basis in decoherence theory? And the answer is this. What the dynamics fixes is precisely the basis in which the appropriate context-dependent mixture for the entire system, instrument, environment complex is constructed. And frequently, the relevant instrument degrees of freedom, pointer readings, water droplets in a cloud chamber, channels in a spin measurement via a Stern-Gerlach apparatus, frequently, those instrument degrees of freedom are roughly position degrees of freedom. Hence the privileging of position pointer bases in decoherence theory. And then finally, a couple of additional observations. In what precise sense is the pure state into which the decoherence dynamics drives the system instrument environment complex? In what sense is that observationally indistinguishable from a mixture over eigenstates? The answer is that pure state is observationally indistinguishable from the appropriate context-dependent mixture over joint system, instrument, environment eigenstates, because as the theorem proves, that mixture gives exactly the same predictions as the pure state for all observables constituting the context. And that is how the illusion of a classical world emerges, ironically, from a thoroughgoing, purely quantum mechanical description of reality. I thank you for your attention.
Thank you very much, Professor Howard. And now we have some questions. Please raise your hand if you have any question. Yes, thank you, Professor Howard, for your nice presentation. I have two questions, one regarding decoherence and the other about the complementarity. So regarding decoherence, do you think that decoherence explains the transition from quantum to classical world?
Yes, I do. That's precisely one of the points, is that as both Bohr himself argued and as contemporary decoherence theory argues, the classical world is an emergent phenomenon within the fundamentally quantum mechanical realm,
Right.
in the precise sense in which this theorem about context-dependent mixtures makes clear.
Right. So in terms of the density matrix, so if we want to go to the details, decoherence caused the disappearance of the off-diagonal terms and leave us with the diagonal terms. And
well, actually, that's not true. That's not true, because that would be equivalent to saying that it yields collapse of the wave packet. And that's just not true. That can't happen because the only dynamics in decoherence theory is Schrodinger dynamics, which is perfectly linear. And so it can't kill off the off-diagonal terms. What it does do is it drives the amplitudes on those off-diagonal terms down to a very, very low level. So in other words, it's as if they had disappeared, but whether or not they have well, they don't disappear. They're just lurking there, at that very, very small level. And this is manifest in the following way. There's an inherent cycle time in these decoherence models. And if you have a situation where you've, which is typical in decoherence theory, the cycle time could be many times the age of the universe.
Age of
But
the
one can
universe.
also construct in which case it seems as if as off-diagonal terms never come back. But you can also have situations where the cycle time is on the order of just seconds. And this is beautifully modeled in some of the work that Zurek has done, where he just has these beautiful graphic reproductions of this, where you see those off-diagonal terms decaying, and you think they're gone. And then if you just sit for a moment or two, suddenly the off-diagonal terms come back again. So
Right.
again, this brings me back to the point that the choice of the name decoherence is so unfortunate, because it leads so many people to think that decoherence theory, that decoherence dynamics gives us genuine decoherence, when it doesn't do that. And this
Right.
is why I refer you back, for example, Schlossauer's book, so that
Yes.
off-diagonal terms disappear.
Right, they get very small. And one question was, I wanted to ask that at what point, without a collapse theory, at what point decoherence explains the choice of one of the diagonal terms? Because if one of the diagonal terms is not preferred, we don't get to the classical world.
So this is another interesting question that I address at some length in the paper. I didn't talk about it in the talk, and that is how to put this. We think we see a determinate result, but we are ourselves part of that object, instrument, environment complex. So we ourselves can't be in a definite perceptual state. So this is another place where there is an illusion of classicality, when in fact it's not really there. And again, I would refer you to the paper. I talk, and I give some specific examples there.
Okay, perfect. And am I allowed to ask the second question, the organizer? If so, yeah. My second question was about complementarity and entanglement. Do you think so? So Bohr insists that the role of measuring device and the observer is essential in quantum theory. Do you think that the world would be different without human beings? And how was the world before human beings were around?
So you might remember early in the talk, I said that there were different points of view within the Copenhagen community. Heisenberg, Jordan, and some others both believed in wave packet collapse, and they believed that there was a privileged role for the subjective observer. But I also pointed out that Bohr and Rosenfeld and a number of others following Bohr's lead denied wave packet collapse and did not assert that there's a privileged role for the subjective observer. So this is another myth about Bohr. He never, anywhere, literally said anything about the role of the human observer. He always chose his words with extreme care, and he always used expressions like the agencies of measurement, meaning the literal physical measuring instruments. He literally never talked about a subjective observer. Von Neumann did, lots of people did, but that was never part of Bohr's point of view.
I see.
And I'm sorry, but that's such a widespread confusion about Bohr. And it's because people read the secondary literature and they don't read Bohr.
And Bohr does not consider human as part of the measuring instrument, right?
Oh, the human is a physical system. But in that respect, the human is in no way different from a Stern-Gerlach apparatus. It's just the human observer is just another physical system. So again, it's especially important that he said nothing about a privileged role for the subjective human observer. Heisenberg wrote about that all the time. Jordan wrote about that all of the time. But that was never part of Bohr's interpretation. Let me refer you on an early slide, and get the slides from Hamid. I gave the citation for the article on the Copenhagen interpretation that I just published a short time ago in the brand new Oxford Handbook on the History of Quantum Interpretations. And I lay out in that article in great detail what were the very detailed differences among all of the members of the Copenhagen community, and with lots of citations to original texts. And I think you might find that to be a very, very helpful article.
Sure, sure. Thank you very much.
It seems that there is no more question. Thank you very much, Professor Howard.
Well, thank you very much.
It's an honor that you accepted our invitation, and I wish you all the best. Good luck.
Okay, thank you.